Predictive control of switching power converters. Predictive controllers rely on optimum control systems theory and aim to solve a cost-functional minimization problem. Predictive controllers are relatively easy to numerically implement, but electronic power converters are nonlinear time-varying dynamic systems, so a different approach to predictive must be taken. Principles of nonlinear predictive optimum control. The first step to design a predictive controller is to derive a detailed direct dynamic model including nonlinearities of the switching power converter. This model must contain enough detail of the converter dynamics to allow, from initial conditions, a forecast in real time and with negligible error, of the future behavior of the converter. Sliding mode control of switching power converters chooses a vector to reach sliding mode as fast as possible high switching frequency. It would be better to choose a vector to ensure zero error at the end of the sampling period t. To find such a vector, a previous calculation can be made prediction. The converter has a finite number of vector states and is usually nonlinear. One way is to try all vectors to find the one that minimizes the control errors, prior to the application of that vector to the converter. Direct Dynamics Model-Based Predictive Control DDMVPC. Receding Horizon Optimum Predictive Control. The algorithm. Obtain a dynamic model of the converter. Example. Define a quadratic cost functional JJT, thus J, and its weights I, UPWM. Sample control variables and selected disturbances at sampling time Ts. Use a prediction equation, from the direct dynamics, to predict the value of the control variables in the next sampling time TST for all converter vectors USJ. For each vector, calculate the cost function JJT, USJ, and determine its minimum. Apply the new vector, advance to the next sampling time, return to step 3. Inverse Dynamics Optimum Predictive Control IDOP. Fast Optimum Predictive Algorithm. Obtain a dynamic model of the converter. Sample control variables and selected disturbances at sampling interval t. The control objective should be attained at sampling time tt, then ITT equals IRF. Use the Euler backward method to obtain. Use a prediction equation from the inverse dynamics to predict the value of the optimum control vector USTT in the next sampling time tt. Calculate and minimize a cost function that evaluates the distance between the optimum vector USTT and all the available converter vectors USJ. Apply the new vector, advance to the next sampling time, return to step 3.